Alright, take out your notes. No. Hey, actually not a very nice gift. Not your idea, oh my god. Very funny. Because I asked someone yesterday, and then she said Lego bouquet flowers. But it actually looks good. I thought it's like one Lego. I know, he already has the details. So, oh, thank you. Yes. Well, but yeah, I bought the flowers like immediately. The flowers that never die. Because I hated flowers, right? But then this is actually a pretty good gift.
Is it X?
$70. But flowers that never die. Yeah, you can start online. It's like they show you the whole bouquet because I haven't built it yet. Lego bouquet flowers. You had to build it. It's like very fast one, but I haven't built it yet. So I was thinking, right, whether I should build it first or we should build it together. That's what everyone says. So I look forward to it. Okay, anyways. Why is my thing not? Hate it. Hate it. Why? 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 That's show. So nice.
Is it from Nicola?
What? What little food? No lah, a bit only lah. Okay, come, let's just start for today. We are gonna continue from page 20 onwards. Let me recap what we did last lesson first. This lesson a lot more important because mechanism. Okay, I will finish up the notes. Okay, I won't be touching tutorial today, no time. Okay, quick recap of what we did last lesson. We went through the idea of synthesis and reactions. Synthesis of halogenal alkanes means you can create a halogenal alkane from something. There's only like two reactions, FRS and electro-N. Remember, right? Okay, but what's more important was reactions because this one contains new reactions that we have not seen before. Okay, halogenal alkanes can turn into other stuff. Main reaction is this thing here, nucleophilic sub. We didn't touch on mechanism last lesson, but we did cover 3 nucleophiles under nucleosub. Can you all remember what are the 3 nucleophiles? Okay, the CN minus, that's the second nucleophile. What else? OH minus, okay, there's one more. That one where we went through like 4 different reactions. Okay, that one is ammonia. This is the one, right, with multiple substitutions. So that's the one that's slightly confusing. You need to read it a few times before you can actually get it. Okay, there are other than that, right? It can also undergo elimination. It's slightly different reaction that gives you an alkene instead. Okay, can? That's pretty much all we went through. All the specifics and all that. Okay, you can look back at the notes. Okay, but for today, I'm going to go straight into nucleophilic sub. The mechanism is probably the most tricky one compared to every other mechanism. Okay, because there are actually 2 types of nucleophilic sub. SN1 and SN2 nucleophilic substitution. So there's 2 variations. We're going to understand every single property. Because this one is very important. If you don't remember a property of a reaction, right, you can't identify whether it's SN1 or SN2. Everything will just be wrong. Okay, so on page 20, right, we're going to first start off with SN2 mechanism. I want you all to take a look. There are 5 properties, correct? I'm not going to go over each and every property one by one like that. I will eventually touch on it as a whole. Okay, SN2 first. Okay, so guys, when you see the word SN2, I need you all to take note. What does the 2 actually represent? Okay, second order, yes, okay, correct. Okay, but let's be a little bit more specific. There are 2 reactants in the what? Okay, slow step. Or rate equation, yes, both are the same. Okay, so yeah, second order 2 reactants in the slow step. Now, why I have to tell you all this is because a lot of people see the word 2 and they think it's a 2-step reaction. Now, that's not correct. Okay, we'll get to that later. But when you have 2 reactants in the slow step, it means the rate equation will consist of 2 items. And both of them are first order. Okay, that's why overall it is second order. Okay, you have a halogenal alkane and you must have a nucleophile reacting with it. Nu for nucleophile. Okay? So there's going to be a bit of kinetics involved in this topic. But not to worry, okay, it's all there you have seen before. Alright? Now, other than having 2 reactants in the slow step, right, it's actually considered a 1-step reaction. That's why I need to lay this at the start. 2 means the rate equation, not the number of steps. Okay, later we will see why it's a one-step reaction. Okay, and other than that, the third property is SN2 is generally favored by primary halogenal alkenes. Generally favored because there are some exceptions that we'll cover at the end of both mechanisms. Okay, later on there will be one segment where I give you guys a plain piece of paper. We're going to do stuff that's not really in the notes. Okay, so I'm going to cover 3 out of 5 first. The other 2, right, we'll eventually talk about it. So I need you all to turn over to the next page. Okay, go over to page 21. I think there's a big fat box there. Okay, we're going to draw the mechanism. Now take note, I personally think that SN2 is the hardest mechanism to draw because there's a lot of specifics. Okay, quite steep learning curve. Now what's the first thing you need to write in your box? Anytime you draw a mechanism, what's the first thing? Okay, the name, right? The title. Okay, so guys, do not just write nucleophilic sub. That one is wrong. Here you need to specify whether it's SN1 or SN2. Yes, clearly, okay, they are drawn very differently. So what I need you guys to do first, okay, give me your title, SN2 nucleosub. Now I write in short form, but I expect you guys to write the full thing because you cannot write short form in exam law, of course. Okay, I need you guys to follow the steps very carefully because there's very, very small details. Number 1, I need you all to position the 4 bonds on carbon like this. Exactly in this shape. Okay, of course, this is tetrahedral, but this particular shape right here, okay, must be shown like all 3 bonds are facing the left, but there's 1 bond facing the right. Okay, the shape itself is very particular. Now let's fill in a primary halogenal alkene since that's what's normally favored. So I only have 1 alkyl group, and then I have the halogen here. Let's just use Br, and then the rest are just hydrogens. Now one simple question now, guys, is this carbon chiral, the middle carbon? Okay, it's not because you have 2 H's, right? Okay, but this is the misconception a lot of you guys have. Okay, a lot of you guys think, right, that you draw stereochemical formula only if it is chiral. Okay, that's not true. Stereochemical, right, this formula here is for any tetrahedral carbon, whether it is chiral or not. So just draw it in this case. Okay, I should have told you guys to leave a bit of space on the left because I need you all to draw a nucleophile OH minus on the left-hand side of this compound. Yeah, I always forget to warn you guys now. Then you end up drawing this all the way on the left, then you don't have any space. Okay, I'm so sorry about that. I always forget to mention. Okay, never mind. You can, as long as you have enough space to attack from the back, can read. So helpful. Okay, yeah, and guys, anyways, a mechanism need to draw in pencil. Okay, in exam, please do not draw it in pen. Okay, can first. Okay, there's a reason why we need to attack from the back. Okay, so before you draw anything else, I need you to tell me who's rich and who's poor. At the end of the day, that is the flow of electrons. Who's rich? Okay, the minus charge. Okay, so this is the nucleophile is rich, meaning this guy has to be poor. Last lesson I went through, what part about this molecule is poor? Okay, there's one atom particular that is poor. What is it? Okay, remember, anything that is poor generally has a partial positive charge or a full positive charge.
Wait, nucleophile is OH minus.
Yes.
Because is.
Okay, so there's a negative charge there and there's a lone pair on oxygen, so that makes it rich. Okay, so we just need to draw a lone pair, but then the carbon, we mentioned, right? The carbon that's bonded to the halogen has to be poor because that's the only polar bond you can find. Right? So that particular carbon has a partial positive. The arrow should be very obvious. Start from the lone pair and attack the carbon like this. Okay? Yes, must draw lone pair. Why? Arrows represent the movement of what? Electrons. If you start from oxygen without drawing lone pair, I can't see anything, man. There's no electrons there, so it's wrong. Okay, guys. Currently, the carbon in the middle has how many bonds? Including the red color arrow, it is 5, right? Okay, so clearly carbon cannot hold 5 electrons. What must happen also? Okay, what bond do I break? Okay, CBr. Now, of course, Br is stealing this bond over here of electrons, right? Because it's more electronegative. So might as well just break the bond and give it to him directly. Okay, remember the specifics of your arrows. So I always emphasize, draw bigger so that you have no room for ambiguity. So you can see that this bond of electrons starts from here and goes towards Br. Hello. Okay, can? 2 arrows only. So it's just attack and break. So the bond forming and bond breaking happens simultaneously. So that's your first step. Currently, any questions? Okay, so you can see this right here is the slow step because I have 2 reagents in the slow step. Okay, it conforms to SN2. Okay, so far? Can Okay, the next step, very important. So follow me first before I let you all draw. What we're going to experience next, right, is not the final product. If you all remember from your school notes, right, I'm now going to draw this thing called the transition state. Now, what is this actually? It's the first time that you guys are exposed to this. So you can think of it this way. Okay, imagine this carbon, right? Okay, and this Br is a couple, right? And then suddenly maybe the guy, right, stops giving the girl enough attention. So clearly the girl is not very happy. She wants to break up, right? She wants to get together with someone else. So that's what she did. Okay, she can find someone better. And of course, that means she has to break up with her current boyfriend. Now, of course, it's not very simple in real life, right? Okay, there's always that period where she's still considering whether to break up and also considering whether to get along with this other guy. Meaning to say, this is like the stage where nothing is really confirmed yet. The nucleophile hasn't really gotten with the carbon, and the carbon hasn't really broken with the bromine. So this is the period where nothing is confirmed yet. So this is the transition state. Everything else remains the same. So I want you guys to notice now the shape, right, looks like a stick man. Looks like this. Okay, looks like a stick man. So I need you all to draw this. I think it's on page 21. Yeah. Okay. Okay, guys, follow me. Okay, follow me on this. The normal bond is gonna be on top. But pay attention to the solid and dash bonds. I'm going to now swap the positions of the solid and dash bonds. Like that. Okay, guys, just notice first, I repeat one more time. Do you all notice, right, that the solid bond is on the right, the dash bond is on the left? Now, the solid is on the left, the dash is on the right. They have swapped the order. Now, there's a reason for this. We'll go over this reason later. It's part of the property of this SN2 nucleoside. Okay, so imagine this stickman character looks like a person. Okay, so this shape is called a pentavalent transition state. Okay, don't you know the name? Okay, what I'm trying to say is just remember the shape here. And the bonds that are not already formed or broken yet, right? Just use dotted, like dot. Okay? Any issues so far? Okay, but then of course, after everything has happened, right? After she has taken the time to consider, eventually she's actually going to break up with her current partner and get together with the new person. So now, take a look at the shape of the molecule. When oxygen gets together with carbon, every other bond now faces the right-hand side, like this. Now you compare this with the starting shape. Just now, the starting shape, everything is facing left, but now everything is leaning towards the right. Again, this is a property we'll go through later. Notice also, the solid bond and the dash bond has swapped positions. Just now it was right and left, now it's left and right. At the same time, your Br is actually going to come out and it's going to be Br minus. Why does he now gain a negative charge? Because guys, can you all see? He gains electrons. Gaining electrons means you have a plus charge. Sorry, when you gain electrons, you will have a negative charge. When you lose electrons, you will have a plus charge. I mentioned this before. The charges, right, very easy. You just take a look at your arrow movement in your mechanism. Okay, can I take your time to draw this first? That is the whole SN2 nucleoside. Okay, later we'll practice more. All good so far? Okay, I'm not done with the properties yet, right? So we still have 2 properties to cover. I'll cover only one more from this mechanism. Any questions so far? Okay, I think there's a little bit of fluke over here. If I were to put my carbon over here instead, right? And my H over here, okay, I think this will prove the point a bit clearly. If I swap the orders, right, the solid bond will still be CH3. Okay, the solid bond is still CH3, the dash bond is still H. Okay, perhaps this will look a little bit more accurate. Okay, so whatever atoms you assign to each bond, right, just stick with it throughout. Okay, then over here, same thing. This is CH3, this is H. Okay, the order just holds. Okay, so if you want to be a little bit more specific, right? Okay, then this one will be more accurate. No, you can assign all the atoms to any bonds you want. Okay, it's only the halogen, right? Just put it on the right hand side because you want to break it eventually. Okay, but whatever you assign, just make sure you stick with it throughout the entire process. Okay, then. Right, so those were done, right? Okay, you all can turn over to the previous page. Okay, just now there are some properties, and we're gonna go over one more. Now, from this, right, you all notice there's a lot of flipping here and there. All these small little details, which I'll test you guys on later. Why does this happen? Okay, so you can see the flipping. This is known as the inversion of stereochemistry. The whole configuration can flip. Why? Okay, so take note. The reason behind it is due to the nucleophile's rear side attack. Now, there's a reason why it attacks from the back. Okay, it's kind of a little bit like steric hindrance. It cannot attack from the front because bromine is a very large atom, correct? All the halogens are very large. So it's blocking a lot of the space from the front. So the nucleophile has no choice but to attack from the back. So for SN2, you need to show the rear side attack of the nucleophile. If you attack from the front, if you attack it from anywhere else, they will mark you down. Very specific, very, very small details. Any questions so far? Okay. Another thing, okay, so look at the properties, Guys, you look at this mechanism that you guys have drawn. Does this look like one step or two steps to you all? Okay, it looks like two steps actually, because there's a slow and fast, right? So this is a lot of what you guys think. Why is that this is still considered one step? Because I need you all to take note, right? We form a transition state in between. And a transition state, right, to put it very simply, though without going into any details, doesn't actually exist. In other words, a transition state is a purely hypothetical structure that scientists just come out. I have no idea why also, let's not question it. But you still need to draw it. Okay, despite it being hypothetical, I need to see it being drawn in your SN2 mechanism. In other words, you cannot actually synthesize a transition state in real life. Okay, I realize there's one small detail missing from my diagram as well. The transition state must have a negative charge. A small little detail that I missed. Guys, why is there a negative charge? It's because of what? What caused the negative charge to appear? No, not really, it's the OH minus. Guys, can you see, right? You need to balance the equation, correct? So if there's an OH minus at the start, okay, here must have minus, here also have one minus. All about balancing. Okay, so far? Yes. Yeah, you cannot create this thing in real life. It's just purely theoretical, right? Okay, but we still need to draw it. And because it doesn't exist, right, y'all can treat it as if it is one smooth step. I know it's split into slow and fast now, okay, but only the slow step here matters because you have two reactants affecting the rate. Okay, so far. And with that said, right, I've covered 4 out of 5 properties. You can already see, right, the 5th property that I didn't touch on, that one is related to explain why primary halogenial alkanes tend to favor SN2. I will cover that later on. And so far? Any issues? Okay, now that that's done, okay, there's some small little things here like on page 22. Okay, page 22, I need you guys to draw in this energy profile diagram. Come, let's draw this together. Can y'all remember what's an energy profile diagram? Let me give you guys 2 shapes. Is it this one or is it this one? Okay, good. It is the first one with humps. The second one is what? Okay, that's the Boltzmann distribution or whatever you call it. Okay, Boltzmann distribution diagram. Okay, so please recall. Okay, so we are drawing the hump version. Can you guys tell me what the x-axis? Sorry, can you tell me what the y-axis is first? Why is more important? Energy profile diagram, right? Okay, so energy in kilojoules per mole. And the x-axis, can you remember? Okay, good. Progress. Okay, the reaction path, the progress of the reaction, anything, whatever. One question. How many humps? How many? Why? Okay. 1 step reaction. Okay, guys, take note. The number of steps corresponds to the number of humps. So I want you guys to just draw 1, something like that. Now, as you guys have noticed, right, I have assumed something. Okay, but you will see it when I label everything. Okay, guys, anything that I need to label here, or I can just leave it like that? Okay, tell me what to label. Inside must know what. Okay, there's how we all said mentioned two already. There's the delta H, right? So the enthalpy change here is exo or endo. From what I've drawn. Okay, it's exo. I'll explain why it's exo in a bit. Right now, you all just fill it in first. So tell me delta H is less than 0. Okay, there's something else as well, right? The activation energy. Okay, so this one you should know by now. You go from the reactants to the top of the peak. That is your EA. Anything else to label? Okay, the reactants and the products. Okay, guys, don't ever write there reactants and products. Okay, go and specify what reactants. So you already have it here. Okay, so what I want you guys to do? RBr and OH minus. Okay, don't need to draw the whole thing. Okay, then afterwards, after substitution is ROH and Br minus. Can you see that? Okay. Now, usually this is enough. Okay, but now, right, I want you guys to tell me where do you think the transition state is located at on this diagram? Just make a guess. Okay, it is at the peak because that's literally beside, in between the reactants and the products. Now, there's a reason for that. When we go through SN1, then I will explain more. Right now, just write down transition state. If you want to draw it out, can, but I think they won't give you extra marks or anything. Okay, just label minimally. Okay, again, transition state in your syllabus. It is a very, very weird concept. Okay, that's very abstract. Okay, we won't go into it too much, which is good, luckily. All right, so that's. Any questions so far? Okay, can. Okay, guys, the box at the bottom of the page, I'm going to ignore because later, right, I think there's a better way of going through this. Okay, so ignore this first. Okay, let's move on. Okay, page 23, I discussed already, inversion of stereochemistry. Okay, so that's done. Okay, go over to page 24 now. I want you guys to consider SN1 mechanism. Right. Without doing much, okay, let's just guess the properties. Okay, don't even need to look at the notes. Okay, take a look at the board. Okay, 1. SN1 means what? What does the 1 mean? One step? Okay, good. Okay, please take note. Establish this first. I only have one reactant in the slow step. Never ever tell me there's one step. Okay, that's a massive mistake. Okay, one reactant in the slow step, you want to make a guess which one it is, the halogenal alkane or the nucleophile. Which one more important? Okay, of course, the halogenal alkane. Okay, you can kind of make do without the nucleophile first. Of course, you need to have an RX inside. Okay, so how many step reaction is this? Okay, it will bound to be a 2-step reaction. So the number of steps, right, actually is opposite of your number. Okay, so once SN1 will be 2 steps. Okay, as for why there are 2 steps, okay, later we look at the reasoning. And generally, it is favored by tertiary halogenal alkanes. Now we missed out on secondary, right? You guys want to make a guess? Secondary favors which one? Okay, we only have 2, SN1 and SN2. SN1 is tertiary, SN2 is primary. Secondary does what? Okay, it kind of has both. Right? Secondary halogenal alkanes undergo a mixture of both. As for which one it undergoes, it's not to say that they won't test you guys on secondary. They will test more secondary. But that means you cannot just use a convenient assumption like this to assume which mechanism it undergoes. Okay, you must look at the properties. You need to know the properties by heart. You identify some clues like these, right, to see whether it's SN1 or SN2. Never mind, later I'll show you guys. Okay, can so far? Okay, next. Okay, there's also some other funny property regarding its stereochemical formula. We'll do that later. Okay, as for right now, what I need you all to do, okay, go over to the next page, draw the mechanism. Again, title first. Okay, let's get it out of the way. Yeah, there's a reason why halogen derivatives is one of the core organic topics because of SN1 and SN2 nucleoside. Okay, content-wise is also more. Okay. Okay, thankfully, SN1 is not as detailed as and not as strict as SN2. It's much easier. So SN1, I can never see errors. SN2, if got errors, I can understand because it's very, very tricky. Okay, so there's 2 steps. So immediately go and draw 2 steps first. And because we are looking at a tertiary halogenal alkane, okay, let's draw a tertiary also, right? Tertiary looks like this. You want to draw structure also can, but again, I always prefer skeletal. Right? Okay, the previous one can draw skeletal as well. Okay, but because there's so many little tricks and details, right, I avoided that. You can if you're better at it. Okay, once you get good. Okay, that's all right now. Just now I have to go through all the atoms one by one. Okay, nothing, no one's stopping you from doing skeletal. Okay, guys, do I draw the nucleophile in the first step? No, okay, I mentioned the nucleophile is not present, right? Okay, so what happens over here? I need you to note. Because this bond here is polar, right? Just like just now, the carbon will just break its bond with Br unprovoked. So there's no nucleophile attacking the carbon to force it into breaking the bond. It just breaks apart by itself. There are many reasons to explain this, okay, and we'll eventually touch on it. Okay, one simple reason is this. Okay, do you think electrons are stationary or always moving? Electrons are always moving, right? And we know that in this bond, electrons are favored towards the carbon or bromine. Bromine, right? So there is any one point in time, right? The electrons sway here, sway there, and then it just goes too much towards bromine, and that's when the bond finally breaks. That's one explanation, but it's a more appropriate explanation later. Okay, but what's going to happen now, right? I need you guys to try to tell me what the products are. Of course, slow step. What happens to the carbon that just broke its bond? Okay, plus, good. Okay, because he has just lost electrons. So I need you guys to show me this thing here. What's this thing called? Carbocation, good. Okay, it is just a carbon with a positive charge. Go and write this down. This is a carbocation intermediate. Now notice, just now we drew a transition state, but now this is an intermediate. Can we synthesize intermediates? Yes, it's possible to create this thing, even though it is a very unstable compound, right? Okay, it is still possible. Okay, unlike transition states, which exists for only a split moment, right, then it disappears already. Right, Ken? Okay, then of course the second step is very simple. Okay, right now we have a carbon with a plus charge. What will attack this carbon? A what? A nucleophile. Okay, we're just going to use OH minus, same as before. Please show your lone pair, and I want you guys to attack the carbon like that. Not the positive charge. I know some of you guys have a habit of drawing too small. And when you draw too small, I sometimes see the arrows and the plus charge like squeezing in that one corner. Okay, no, okay, to avoid any ambiguity, I suggest put the arrow and the positive charge on opposite sides of the structure. Then at least, right, I can clearly see what you're doing. Okay, then once this is done, very simple, just label your fast step, and you have my new compound. Okay? No need to draw stereochemical formula here because there's no inversion or any funny shit happening. Okay, very simple, just draw skeletal. Arrows, simple also. Any questions so far? No, okay. Once done with that, okay, we will proceed over to the next page. Yeah. Okay, OH minus is just a nucleophile we use to substitute. It's part of the reaction already. It just doesn't appear in the slow step yet. Yeah, that's why it's not inside. Yeah, okay. OH minus is the nucleophile that you react with. Okay, it just doesn't appear in the slow step. It appears in the overall reaction. Can? Okay, now the next part, also very simple. I need you all to draw the energy profile diagram. Okay, page 26, okay, draw the same thing like what we've drawn just now, right? Yeah, I didn't explain why it was exothermic. We shall do that now. Right, how many hums do we need to draw? Yes. Okay, we need to draw 2 hums, because this is a 2-step reaction. Why is it so sharp in the middle? Okay, you should draw a line because you need to write stuff on it. Yeah. I mean this works as well, I guess. Oh, nice.
Thank you.
Very nice. Artistic skill.
Thank you. Thank you.
Okay. Have fun, have fun.
I'm not Oh yeah,
Okay, so I want to see two harms. Which harm is higher, first or second? Okay, definitely first. Okay, I want to see an overall exothermic reaction as well. Okay, some small little things. Okay, notice how, right, I have three lines. Okay, first line represents the what? Reactants. Okay, so reactants in this case is this guy in. Yeah, sure. Okay, guys, take note. To label the reactants and products and all that in the energy profile, I think some of you guys might be a bit tricked over here. Okay, notice, guys, do you all notice my first step only has one species, but I end up drawing two? Okay, do you all notice I draw both here? Because I need you all to make sure that all the reactant, intermediate, and products are balanced with each other. In the slow step, fast step, right? Okay, later we will combine everything in order to form a balanced equation. Okay, later you see what I mean. Okay, but I think a lot of you guys will just put the halogen alkane because that's what you all see in the first step. Okay, never mind. Okay, later I'll show you all first. Okay, in the intermediate step, I want you guys to draw the carbocation. What else? Br minus and OH minus also. Because I need everything to be balanced. Can you see the OH minus? Does it do anything from here to here? Is it doing anything? No, it's just sitting there. It's just happy to be there. Right? Okay, just there. And then only in the final step, then it becomes this. And the Br minus, did it do anything from the intermediate to the product? Did it do anything? No. So again, right, guys, you notice is every step balanced if I do this? Yes, it is. Conversely, if you guys followed the mechanism strictly, meaning the first one you all draw this only, second one you all draw this, is it balanced so far? Okay, look at the red ones. This is what you probably would have drawn. Because you see, first step only have one item, so you draw one item. Is this balanced so far? It is, right? Okay, you just detach the bromine only. But the final step, what do you all draw? That's the thing. Do you all notice I technically have two intermediates to draw. Okay, but you only drawn the one over here. A lot of you guys jump straight to the products and you draw this. Look at the red colors. Are they all balanced? Where's the OH here? Where's the OH here? And where's the Br here? You see that? So do not follow the mechanism steps strictly. You must still draw OH minus inside. So follow the purple ones where they are all balanced. Can see what I'm referring to. Okay, so there was a kinetics question last year that also similar to this idea. Okay, a lot of people just follow step 1, step 2 and all that. Okay, but you will not end up balancing the whole thing. Okay? Okay, activation energy and all that. Okay, just go and label. Okay, this is EA1. Please make sure EA1 is higher than EA2. Okay. Overall, this is exothermic. We'll talk about that in a bit. Oh, might a bit second, but never mind. Hey guys, can I ask you all, right? Why is it that the intermediate step must be above the reactants and the products? Okay, why must it be above? Okay, let's use this to recap a bit of energetics and kinetics. Guys, when you have a higher energy level, you are what? Less stable, good. Conversely, lower energy level means you are more stable. Now guys, intermediates, are they stable or unstable? Good, take note. Intermediates in general are unstable in nature, right? If not, they will just stay as an intermediate and never turn into anything else. but here it's turning into other stuff. So intermediates cannot stay for long. Intermediates are unstable. So since they are unstable, they must have high or low energy level. High. That's why, right, you have to put the intermediate step higher than both the reactants and products. Can see that? Okay, so some energetics stuff. Next thing. Why is the product, okay, why have I drawn exothermic for both cases? Guys, delta H, how to calculate? Something minus something. Remember? Bonds broken minus form. Okay, let's try to use this to explain now. How do we do broken minus form in this case? Okay, please remember this formula. Okay, what's the bond broken in this whole context? Okay, so CBr or CX in general, CX minus what bond? What bond is formed? Okay, COH, CO. Okay, just say CO. All right, so no matter what halogen you use, guys, can you tell me which bond is stronger? Okay, CO. O is smaller than halogens. You don't believe, just check the data booklet. Okay, so if this guy has a higher bond energy, that means delta H must be negative. Can see that? You're minusing a larger value. So that's one way to explain why the delta H is assumed to be exothermic. Okay, and at the end of the day, exothermic reactions are more common because you're forming a more stable compound, lower energy level. That's another way to explain also. So this one, right, I don't, from my experience, I don't see them specifying whether it's endo or exo. Best case scenario, assume it is exothermic. Okay? Not really done with this yet. This one's more detailed than the first one. Hey guys. Okay, any questions? No? All right, there's a reason why this is two steps, because we form intermediates, and intermediates are technically real compared to transition states, which are fake, I guess. Okay, you look at your intermediates. Okay, where does it occur? Okay, can you tell me just now, where does the transition state occur? At the top, right, the peak of the mountain, right? But intermediate, on the other hand, occurs where? It's like at the cleavage, it's like at the bottom of two mountains, right? Can see that? Okay, we call it a valley. Okay, it's a PG-13, right? Okay, so that's the idea. Okay, I need you all to take this down also. Intermediates occur at energy minimum. A transition state occurs at energy maximum. So just based on this information, guys, in SN1, how many transition states are there actually? We have two peaks, right? Okay, technically we have two transition states, but we don't have to identify those because it's not part of our mechanism. Okay, so intermediate, you all must draw at the bottom of two peaks. Transition state, I need to draw, you all need to draw it at the tip, I guess, right? Okay, so biggest takeaway from this diagram is I need you all to not just follow the step 1 and step 2 blindly. Okay, your reactants, intermediates, products must be all balanced up. Alright? Okay, you all may be asking that how come the step 1, step 2 don't need to be balanced? It's because this is not the overall equation. Overall equation is you take step 1 and you plus step 2. Then that's the overall equation, which is not the case here. Okay, this is all balanced up. Okay, step 1, step 2 not balanced. All good so far? Okay, okay, same thing. The box at the bottom, you skip. We'll touch on it later. Any questions? Okay, we'll practice more of this. Okay, I'll go over one more bit, then we take a break. Very fast. Okay, notice we have 5 properties, right? I've gone through 3. Just now, SN2 was the property regarding stereochemistry. What happened to the stereochemistry? Okay, we'll flip, invert. Okay, here that doesn't happen. Okay, what happens instead? We have this concept that we have learned back in alkenes, and it will appear here again. It's the same exact thing. Notice this part here. This carbon, can I ask you guys, what shape is it? The one with the plus charge. Okay, trigonal planar, very good. So this nucleophile, is it only limited to attack from the top? No, where can it also attack from? Okay, so it's flat, right? It can attack from either the top or the bottom. What are the chances? 50-50. Okay, then you form a racing mixture. Okay, remember all that? Right? Okay, so the explanation for that is on page 27. I'll highlight the keywords for you guys again, don't worry. But right now, okay, I'll look at page 27, right? This box here that we're going to draw, go and write there, it is not examinable. I repeat, the box at page 27, thank God, it's not examinable. Okay, but I want you guys to draw along with me to understand how this racemic mixture is formed as well. We're going to use this chance to recap what's racemic. Okay, that's an earlier topic, so you guys probably forget a few things. Okay? Okay, guys, racemic mixture means what again? Can you all remember the definitions without going into all this yet? Okay? No, just racemic mixture. I don't want to know how it's formed. What is the definition?
Equal proportion.
Okay, good. Equal proportions of how many enantiomers?
Huh? No.
Two, yes, okay. Equal proportions of two enantiomers. That's it. Okay, guys, a racemic mixture just means this. Nothing about attack top, bottom, optical, don't know what. Okay, no. It's just like that. All right. But a property of racemic mixture is what? Okay, correct. So a racemic mixture is, to put it simply, optically what?
Inactive.
Inactive. Good. Okay, so take note, I repeat again. Equal proportions of two enantiomers, that's the definition. That's it. That's what it means. Okay, and it's just optically inactive. That's a property of a racemic mixture. That's it. Okay. Perhaps we use this chance to recap first. Why is it that we have two enantiomers? They are optically inactive. Why? Guys, can you remember what does an enantiomer do in the first place? Okay, it rotates plane polarized light, but you have two enantiomers related to each other. Normal image, mirror image. What's the relationship between the rotations? Okay, they will cancel out because they rotate by the same angle, same extent, but opposite directions. Good. Okay, please take note. Two enantiomers were related to each other. They will rotate plane polarized light. You don't even know what plane polarized is, honestly, unless you're a physics student. Okay, by the same extent, but opposite directions. Again, guys, I later will tell you what is important to write in exam. Don't worry. Okay, right now I just need you all to understand first. So can you all see how this works? If one image rotate by 15 degrees, the other image will rotate by what? The opposite 15 degrees, negative 15, right? So if you have equal proportions, they will just nice cancel each other out. Can you see that? Okay, so that's racing mixture in a nutshell. But now I'm interested in how this is formed. How does this come about? Right? It's related to what we showed just now, right? It all starts because the carbon is, this particular carbon alone is planar, flat. If it's completely flat, it can attack from both sides with equal chance. That's why you even have this in the first place. Two enantiomers with equal proportions. So come, look at the box. Let's just draw a visual diagram. What I need you guys to do, draw this particular shape inside. Okay, I purposely draw this. Okay, there's a reason why I draw so many carbons, right? How come here got 3 carbon, here got 2 carbon, here got 1 carbon? Okay, eventually the OH minus is gonna attack from 2 sides, either the top or the bottom. Yes, you all know that already.
Okay.
Yeah, okay, that's another thing to consider, right? Okay, but over here, the reason why I draw this particular compound is, any idea why? Why did I draw so many carbons? Why did I draw 3 here, 2 here, and 1 there? What? Okay, guys, take a look. Okay, first of all, racing mixture must have enantiomers in the first place, right? Enantiomer must have the, what kind of carbon? Chiral carbon. That's why I can't use this example to go through because it's not even chiral, right? So I purposely draw 3 different groups. But y'all can tell me, just draw something smaller lah. Just draw like, I don't know, 3R or something, or H. But guys, tertiary. Okay, I'm trying to highlight that this is still under a tertiary halogenoalkane. I can't draw three same alkyl groups, so I draw three different alkyl groups. Okay, there's a reason for everything. Okay, and top, bottom, equal probabilities. Okay, I'll take this down already. I need a space. Right? Okay, so again, thankfully, you don't have to draw this shit. Okay, so let me just follow. Okay, you guys just follow me. You attack from top, you attack from bottom. Okay, we try attack from the top first. Okay, this is just for your own understanding. Okay, visualize if the OH bonds to the carbon on top, then all the other bonds will be flush to the bottom. Just follow that. Okay, so this are flush to the bottom, flush down, flush down. Then just fill everything up. Okay, luckily you don't have to draw this up. Okay, guys, if on the other hand, I attack from the bottom, then all the other bonds will get flushed to the flush up or flush down, upwards. Okay, you can see I attack from the top, force everything down. I attack from the bottom, force everything up. Okay. That. I have two enantiomers now, and they are in a 1-to-1 proportion. Because you attack from the top, 50% chance, attack from the bottom, another equal chance. Now, some of you guys who want to know a bit more, right? You ask me, why are they related to each other? Why are they enantiomers of each other? Yeah, I won't really go over this because you don't need to know. Again, this box don't even need to understand. Okay, but just know that they are related. If you try to orientate them to the correct position, to the same position, right? Like you turn this guy up, right? They're actually different. They're not the same compound. Okay, I won't go through that because it's hard to visualize. Okay, just trust. Okay, what's important is the explanation. So I want you guys to highlight a few things. Okay, whatever that I highlight on the board, you look at the words, or you want to write down again, right? You go ahead. All right, I think it's better. Okay, what's the first point that you need to explain? Okay, usually what is the question? Let's write down a question. Okay, so the product is chiral. You can't deny that, right? But the mixture is optically inactive. Why? What's the answer to this question? Hey, chiral, what? Chiral can rotate, what, right? Then why is it optically inactive? Why does it contradict? It's referring to this scenario. This scenario here. It's because you form a racemic mixture. Okay, how do you form a racemic mixture? Guys, it all starts from what? The carbon has what shape? Okay, the carbocation is trigonoplanar. Please, this is the first important point. I'll highlight that, or just write it down on the screen. Okay. Most importantly, if you don't tell me it's trigonoplanar, right, then none of this can happen really. Okay, so it's trigonoplanar, the nucleophile attack from top, bottom. Okay, just tell me that. Okay, OH minus nucleophile, or whatever nucleophile. Okay, attacks the carbon with a plus charge from both sides of the, you get the point. Okay, both sides of the plane with equal probability. Again, it's not wise to remember word for word. So I again recommend you guys to memorize keywords instead. You memorize keywords, then it allows you to associate it with a certain way of explaining it. More effective. Okay? And then from there, thus a racemic mixture is formed. And this whole thing is just 1 mark. Because why? So it's the same exact answer. It's not difficult to get. Okay? It's never like 2 marks because, oh, you need to write so much. No, they don't give a shit. Okay, it's 1 mark because it's easy to get. It's about how easy it is to get marks. Okay, Ken? Now, last thing I'm going to say, right, before I take a short break, where do you see this question pop up? Okay, write this down. All right. For which topic? Okay, then you all go and consolidate it. So, guys, for example, the cheat sheet thing that I told you all last week, when you're working on it, what will be very good is this. For this question, you can copy down this question in your cheat sheet, you can copy down the answer, and then afterwards you ask yourself, you note it at the side. Yeah, no space. Okay, let me erase this. Okay, you write this out already, then you are like, whoop. Where does it appear? Where can you find this concept? Number one, alkenes. Yes, it was in alkenes. Okay, so alkenes is all because you form a carbocation also. Okay, guys, at the end of the day, it's not about memorizing where the topics, what topics it appears in. As long as there's a trigonal carbocation form, right, you're probably gonna see it already. So alkenes is specifically electrophilic addition. Then next one you see is here, SN1 nucleosub for halogen derivatives. I just put RX for short. SN1 nucleosub. Okay, don't just write nucleosub. Later you go and tell me SN2 wrong already. There'll be one more in your syllabus, one more only. So might as well write down now. You'll learn this 2 topics later under carbonyl compounds. So it's either aldehydes or ketones. That's it. Okay, 3 only. Okay, a carbonyl one will be slightly different actually. Okay, let's not lump this under carbocation. Carbocation only have these 2. The last one that you will see, right, is just a trigonal planar carbon. I think this is a better, just better. Okay, trigonal planar carbon you see in carbonyls. The reaction is called nucleophilic addition. You haven't seen this yet, never mind. Okay, right? 3 places you can find this. I tell you all now, right? Then after that, next time you don't need to like think, oh, where does it appear? Just refer lah. It's right there. Okay. Any questions? Let's take a break. Right?
Is there 4?
4.
Or maybe my C.
Oh, that's each but I always like basic.
I think my
Maybe you want to move in one C.
Only one. Oh, I can't check that. I want to check.
There's a pair. What? Why do you name your child Hitler? Bro. Aravin something. Yo. Why do you name your child Hitler? Is he bullied since young? No, he's already is bullied. No, is he automatically cancelled? No way. Dude, what? Wait, it's in J1 is in like going in your school right now. Oh my god. Oh my god, wait guys, you'll be damn cool, right? Get him to join Crucible. Then we have a student called Healer. ACGC has a student called Healer. We have to get him here now. Wait, anything like us? No. Wait, we need to get him now. Oh my god. I can tell people that I taught Hitler. Guys, I have a student called Hitler. Wow, shit, that's a fun. Hey guys, let's continue. Mental fortitude. Come, let's continue.
Oh yeah.
Alright, okay, we're done with the page. Okay, guys, right now we're done with page 27, right? Okay, on page 28, we're gonna do a little exercise here, right? Oh, yeah, never mind. Give your paper. Okay, this is where I give your paper. Okay, we're gonna draw a mechanical. And use this paper later on because you go through something that you don't have space to write in the notes. Okay. Okay, you can cover page 28. I know they show a mechanism there, but it's like not very accurate. Okay, let me give you guys instructions on what to do. Now, number 1, I want you guys to draw an SN2 nucleosub. Okay, I'll give you guys the instructions. The nucleophile in this case is ammonia. And I just give you all the structure to draw now. Okay, we are gonna use this guy. Look at the shape. Okay, the shape is whatever we did just now. So come, go and draw the mechanism for NH3 SN2. Right? Give you guys a few minutes. Yes. BR, the MR is like 79.9. Okay, CH3 is like 15. So 79 is freaking big. Yeah, it is. Okay, I mean, you can't tell here now. A bit bigger. Right, again, try not to just copy straight from the notes. Of your own memory, try to draw the mechanism. Later, then you check. Okay, after you finish already, then you go and check with your answer. Okay? Yeah, SN2. Just apply whatever we did just now. Oh, no. SN2 is one step. The 2 represents 2 reactors. I don't know. Because they did about that's really represented some location. Don't refer to that. What are you referring to? That NH3. You gotta give me pencil to draw. Why are you using pen?
I just
Draw again. The paper very big.
I win.
I don't probably know. The reason why I asked you to draw any. If you start any you will start. It doesn't just automatically. This if you join any purpose. Yeah, the reason why I'm asking this step towards the end, done any free. Okay, focus on what we found. Yep. Okay, I don't see the partial charges on the first reactor. Yeah, never break also. Okay, can label the transition state. Okay. Okay, wait. Let's suddenly got one more NAC. Okay, see, right? Here the NAC. It must be the N first, right? Because you're bonding to N, not H. So it's H3N. Now, other than that, there shouldn't be a charge here. Again, just swap it around, but be bonded to N. Okay, then your inversion, right? You're not consistent. Right? The solid must be with H3 4 times. But suddenly the solid is now this. Yeah, it must be consistent throughout. Okay, no, the solid must be left and dash must be right. Okay, don't care about the group yet. You care about the bond first. The solid is right, dash is on the left. At the end of the day, must be solid left, dash right, which is correct. But just that the solid must still be CHP. The dash must be consistent. Yes. Okay, the shape a little bit go up. The end try to shift everything, lean it to the right. You get what I mean? Yeah. But okay, it's fine. Not a big issue. The N is okay, the N must be bonded to C, but then the C now is bonded to the H, which is that doesn't make sense. Yeah, here's correct. Yeah, so try to maintain that. There shouldn't be a negative charge. That's fine. Yeah. Yeah, I don't see the partial charges. Partial charges are equal. Other than that, okay, see, you guys are making the same mistake. The bond, right, carbon must be bonded to N, but now carbon is bonded to H, which is what I see here. I know it's not intended, but okay, must have partial negative. So, we did not swap the author here, which is actually fine. I'll talk about it. If I actually swap it, it goes good. And you're still missing an equal of become plus something. Yeah, correct. Okay, so roughly there. Okay, good observation. Good observation. You will explain that. Okay, so here shouldn't be partner house. Partner house is okay, but we'll try with that. So go and retry. Go there's no the ball here I've never seen indicating. Okay, so okay guys, okay, good try, right? So obviously, as you can already see, right, there is a lot of what's you reading? Okay, there's a lot of details. Okay, a lot of small details that you need to practice. Okay, that's why one time you do this one time is really not enough. First things first, NH3 must attack from the back. So I'll do something like that. I need to see the lone pair on N, and I need to see the lone pair attacking carbon. Usually, I realize you guys just stop here. I need to know why he's poor, because he has a partial positive charge along with partial negative. This bond must break alongside it also. Okay? Those are all the details. Next, we have to draw the transition state. You must label slow. Now remember the transition state, this guy hasn't really formed bonds yet. I need to see the N bonded to this. Okay, so if you attack from the left, right, I need this. You have to flip the NH3 position. Haven't really broken with Br also. The rest of the bonds, just draw like a stick man. Now over here, I recommend you guys to swap the order here. Solid now on the left, dash now on the right. Like this. Can see that? Okay, now some schools, right, actually it's acceptable if you don't swap the order here. But I want you all to swap here first so that you don't forget at the end. Okay, you must swap at the end of this. Okay, there should be no charge here. I know I drew a charge just now. But guys, must be flexible. Over here, is there any negatively charged species? No. So there shouldn't be a negative charge here as well. You can label this transition state. If you forget, I think it's fine. Okay, not a big deal. Okay, last but not least, you're going to finally form the bond with N. And all the bonds now are going to shift. Okay, all the bonds are now going to lean towards the right. So like this, lean to the right. The bonds, the order have been swapped. And finally, Br minus. Must get until here so far. However, this is a little bit tricky because some of you guys have mentioned, how come suddenly got one negative charge come out of nowhere? Am I wrong? Is it supposed to have a negative charge on Br? Yes, right? Because it gained electron. So that's not the issue. How come suddenly it's negatively charged at the product side? If this is negatively charged, which is correct, that means it implies this guy must have a 1. Positive charge, where? No, not carbon. Okay, a lot of us say carbon, but carbon is 4 bonds, it's perfect already. It's N. Why does N have the positive charge? Okay, N must have only 3 bonds, now you see 4. So I want to see the plus charge on the N there. Now that's only one explanation. Yes, you see 4 bonds on N, cannot have plus charge. But later I'll come back to that. The correct reason is this. What's N doing? Losing or gaining? Okay, he's giving away his lone pair to carbon, right? By losing the electron, he must now gain a positive charge. Okay, but just now, when we use OH minus, right? It was okay, what? Right? Okay, when we attack the carbon, eventually the OH bond to C. No plus charge on O. Why? Okay, you notice good. Okay, you give away, he should gain a plus charge still, right? But then minus and plus will get neutral. Right? 0. Okay, over here, you're giving, but you imagine this like you're rich, you give money, you'll be like normal. But if you are like okay only and then you give money, you end up poor. Right? Okay, it's the same way. It's just all relative. Okay, so that's how the charges work. The charges don't change or anything. The rules are all the same. Okay, but clearly this isn't the final compound. Eventually, what is the final compound? You can't have a plus charge in that, right? It's not stable. Nitrogen with 4 bonds not stable. That's why here, this next step is not part of the SN2. Okay, it's just an adjustment step. Okay, it's to adjust it such that we can get our final compound. Before you draw any arrows, can you tell me what the N should have? What should we be here? NH2. NH2, the rest are all the same, and then the last H becomes what? HBr. Good.
Because the BR become the. Is it not the minus polarity?
The word polarized is wrong. Okay, but okay. Anyone? Okay. Well, any questions first before I move on? Why is it this? Because N cannot remain as 4 bonds, not stable. It will turn into something else. It will adjust itself until N has 3 bonds. Can see that? So it just loses 1 H. Now, guys, I want you all to try again. With this in mind, I need you all to try to draw the adjustment arrows such that you can get these final products. Okay, the arrow you must try yourself, because sometimes in exam, they will give you shit that you never see before. You must adapt and do on the spot. Okay, to help you guys out, I want you all to draw the 3 bonds on NH3. Like that. Okay, now go ahead. Draw the arrows for the final step, the adjustment step.
Do you want us to draw arrows?
Such that it becomes NH2 and HBr. Okay, 2 arrows. If done, let me check. Right? Arrows correct. Arrows are correct.
Super bad.
Yeah, it must leave the N definitely. That's why 3 becomes 2. Okay. But how does it leave the N? That's the question. H leave the N. Okay. You're getting the idea, Try first, then let me see. Yeah, you're getting the idea already, alright? Always look at your final result. Okay. Good, yeah, correct. Yes. Hey, don't copy, do yourself. Don't copy, if not.
And I think my VR is and
You can let me see your thing. Okay, you're right in the arrow, but the arrow is pointing to a plus charge. Okay, not a lot, it's pointing to the N. Okay, that's correct, but then the H is gonna like segregate, it's gonna separate itself from compound, then it's just gonna floating there. Someone is playing in, right? Yeah. Yeah, correct. If not, he's like sitting there like an orphan, unclaimed. You must make sure there's always a chain of arrows. One thing must lead to another. Yeah. Okay, so here's the answer. Okay, you guys mostly got it already. In exam, right, there will be things like this where you need to draw arrows on the spot. So you must always observe the result. The result is Br gets together with H. So I must see Br, the rich compound, don't pair, if you don't pair, attacking a H. Okay, let's just attack this one here. You can attack any H now. Okay, must attack H first, then they are together. But at the same time, guys, okay, some most of you all got it. The electrons here do what? Give back to N. Okay, point to N, not the plus charge. Give back to N because N is poor. Give him lah, he needs it. Right? Okay, just do that. So this is not part of SN2, it's just an adjustment step. They test NH3 a lot, so take note. Okay. Okay, I want to go over one thing on that. Okay, some of you guys may have seen in the notes. I don't know whether your school have, like some schools have, some schools have something else. Then I just like don't know what is the standard. So let me just tell you all this first. Guys, do you all have a chart of the transition state?
Yeah.
Here. Here, no. Okay, and because there's no chart, right? Some schools you all might see this shit. I honestly have no idea what this is until today. Yeah, just ignore this shit. Okay, guys, if your school asks you guys to draw this, just draw this law for neutral compounds. Okay, I know like EJC must draw both. Then some schools draw this, then other schools don't need to draw at all. Then I'm just like, screw this shit, it's not even that important. Okay, so just don't draw lah. Neutral, don't draw anything. If your teacher mark you wrong, right, legit just scold your teacher, say that what the hell, right? Okay, you mark me wrong for this kind of nonsense. Yeah, see this kind of thing. Okay, let's just move on. Any questions so far? Okay, guys, before we move on to page 29, okay, you can flip over to the next white blank piece of paper, like we're gonna find a fresh page. Okay, we're gonna do something that I haven't gone through just now. Okay, I need you all to draw this table that I draw on the board. Very important segment, very important. Right? So the way the notes teach it is fine, but it's just that I want to do it more detail. Okay, that's why I've asked you all to write elsewhere. We're gonna go over, right, the preference towards SN1 or SN2. Now, as mentioned just now, okay, SN1 is favored by what kind of halogen alkenes? SN1. Tertiary. But SN2 is favored by primary. We have to understand why. Okay. So I want you all to draw this table. First, we have SN2. And then we have SN1. And for each one of them, okay, there is we call it primary halogen alkene, tertiary halogen alkene. Okay, make sure the box is big enough because you need to write a bit of words inside. Okay, don't draw too small, right? Okay, as like what we said just now, SN2 is preferred by primary, SN1 is preferred by tertiary, so put a tick on both. And conversely, SN1 is not favored by primary, SN2 is not favored by tertiary. Okay, of course you must know this bare minimum. This is the general trend, right? Generally, it's favored by primary, but of course, there were bound to be exceptions, which we'll touch on later. We look at the non-exceptions first. Okay? Okay, next. Let's look at the easy one first. Why do you think primary prefers SN2? So I need you all to write down this factor. Your basis of explanation for SN2 is always about steric hindrance. That is your basis for argument. Okay, you want to argue SN2, you must talk about steric hindrance. It's kind of like a GP like portion over here, right? Now that I've told you guys it's about steric hindrance, can you now tell me why why primary favors it compared to tertiary? Okay, because why? Why does it have less steric hindrance? Okay, that's correct. Yes, that's groups. That's it. Yeah, that's pretty much it. Okay, primary likes it because there's less of steric hindrance. And why does steric hindrance have anything to do with SN2? Remember where the nucleophile attack from? The back. Okay, so there's a lot of space constraints already. So imagine there's tertiary. Can it attack from the back as easily? No. Okay, space here is a very important idea because the core idea of SN2 is all about the rear side attack of the nucleophile. So, explanation easy. Primary halogen alkanes have less bulky alkyl groups. Come, describe it as bulky. Less bulky alkyl groups means less steric hindrance, so it favors SN2. Finish. Okay. On the other hand, tertiary, just explain more bulky alkyl groups faces more steric hindrance, and of course it doesn't like SN2 lah. Okay, so it's not for fun. The factor is because of the rear side attack. So with so many groups blocking the freaking nucleophile, you're not gonna have SN2 happening. And it's simple, right? Really, really nothing much. Okay, the SN1 is a little bit more to explain. Okay. You're getting of what the factor is. All right. SN2 about rear side attack, so you need as much space as possible. SN1, guys, what do you form in between for SN1? Okay. Intermediate. Okay, the intermediate is a carbocation, correct? Now, guys, SN1 will then be dependent on the stability of that carbocation intermediate. Okay, so do you want it to be more stable or less stable? Okay, more stable. Everything in chemistry is more stable. You prefer more stable. Okay. So based on this idea, let's do a little bit of extra stuff. Can you all go and draw primary and let's draw it together. Okay, at the side. Okay, let's draw a primary halogenal alkane. Carbocation, sorry. Okay, for example, this guy here. Okay, versus a tertiary carbocation. Like this dude, for example. Okay. All right. Okay, with those diagrams, right, I hope it helps. How do you know which one is more stable? Or which one is more stable? Okay, tertiary is more stable. Why do? Okay, good. Having more electron donating alkyl groups means the positive charge is good. Okay, dispersed to another extent. Yes. So you just go cut there. Okay, good. You see, you only have one person donating you money versus 3 people donating you money. Remember, this carbon is rich or poor. This carbon is poor, it's a plus charge. So you want more people to give you money, right? You're poor. Okay, so that's the idea. Okay, explanation here more particular. Tertiary has more electron donating. Don't describe it as bulky now. Irrelevant. Alkyl groups. Means you disperse the positive charge to a larger extent. And hence more stable carbocation. Guys, the opposite, just go and write. Same thing. It technically is, but I just prefer this way of going through. Yeah, it was the box that we skipped just now. Yeah. Although this will give you a more comprehensive outline. And whether you want to put this in a cheat sheet, answer is obviously yes. Okay, this is clearly much more summarized. Okay. Yeah, when you do it in a cheat sheet, don't just copy and paste from what you did today. Try to come up with the answers yourself. The box. Like you draw this box, you draw the table, then you go and write it out yourself. Okay, guys, you disperse what? What's the opposite? What was the word you use here? Guys, are you intensifying the positive charge? Yes, that's the opposite of disperse. But look, is he giving electrons? He's still making him less poor, right? Which is still a good thing. It's just that it's not as much as this. Can see that? Okay, just write smaller extent. Yeah. Okay, don't anyhow use the terms interchangeably. He is making the positive charge smaller. Just to a less extent than tertiary. Okay, so it's the less stable carbocation in comparison. So you don't really favor SN1 because of that. Yeah, of course, you should have a lot more space on paper. We're still gonna go through a few things. Okay, I'll copy out now. Yeah, I mean that's true. It's still part of it also. Never mind, I tell you what to add. Again, if you don't know what to add, never mind. You can add as much stuff as you can. You add a lot of things, right? Never mind. I'll tell you what's not necessary, no, right? 3 reactants, technically, electro add. Mild oxidation, strong oxidation.
Oh, sorry. Wait, let's see. Okay.
Okay, guys, can you write down these two questions? Sample questions.
Put it in here.
Yeah, you can put it. Oh, this you have next page. Oh, sure. Okay, we're not gonna answer this. We're gonna answer this verbally. Okay. This one, right? We're not gonna write the full answer because you already have all the answers in the table. You just need to refer to which quadrant is your answer. Just right there, refer to quadrant 3, 4, whatever. Okay, but there's a bigger point in all this. Okay, let's look through this together. Why does primary halogen alkane not favor SN1? Okay, can you tell me where's your answer from the table?
The
Yeah, it's easy because you have this table right in front of you. But in an exam, right, let me tell you a problem that you guys might fall into a trap. Okay, follow me in this first. Okay, later you can copy. Why does primary halogen alkane not favor SN1? Oh, it's because it favors SN2 instead. Can we answer it this way? Correct, we'll just answer that, right? No, okay, guys, are you answering the question? The question says SN1. You must argue why it doesn't like SN1. So as I say, right? Okay, someone asked me why do I not like coffee? Or because I prefer tea instead. No, you're not answering the question. Okay, so tell me that, oh, I should be saying coffee tastes like shit, so I don't like coffee. Go, you must answer, right? Okay. So over here, why does tertiary halogen alkane not favor SN2? Can you tell me, oh, it's because it prefers SN1 instead? No, cannot. Now it looks obvious here, but how do you not fall into this trap? So guys, I need you to circle SN1 and SN2. If the question print over there SN1, I need you to talk about what? What factor? Yes, stability. Do not mention an ounce of steric hindrance in your answer. How about the second question? Must talk about what? They print over there SN2. You tell me about steric hindrance only. Don't make a mention of stability at all. If not, you will end up in that trap. This is how you answer the question. I'll tell you this first, okay? Then we're gonna try example questions. Okay? Wait, write it. Okay, we're gonna try some sample questions. I will delete the table. Okay, find space. Not enough paper, you can just ask me. Okay, sample question 1. Guys, do you need to put these sample questions in your cheat sheet? 100%, because these are applicable, right? So
very well.
wait, fine. Very common compound. Very common. Okay, later we go over the answer. Later we'll do a sample question.
Quick over now.
Okay, try the first question. The second one, just copy down first. Okay, don't need to do it.
Wait.
Yeah.
Like, don't bring up the other thing. But if you compare it,
What do you mean?
like, yes, less bulky or coverage compared to tertiary.
Okay, when you talk about bulky, right, you're already going in the direction of stereo hindrance. Okay, so for this first question, right, what did the question mention? SM1 or SM2? SM1. SM1, you talk about stability, right? So don't even make a mention of bulkiness or stereo hindrance at all. It's to avoid all this confusion. If you end up writing both, right, I don't know whether you're answering the question or not. Right? Okay, so to be very straightforward, just follow this. Question, print what? You follow that. Yeah. Okay. Look at what the question prints. Right? Yes, it does. It does. It is, okay, but how does it donate electrons, right? It doesn't just donate electrons like an alpha group. There's something about correct. Okay, come, let's go over question one since we are pretty much there. Okay, before we talk about answers, we talk about the answering technique first. Guys, here what do we discuss? Stability of stereo hindrance. Okay, good. The question print over here, SN1, you follow. As you can see, this is a primary halogenal alkene. By right, it should undergo what? You expect it to undergo SN2. Perhaps you can annotate. I expect it to undergo SN2. But the question challenges that. It says that I undergo SN1. And SN1, since the question print right there, don't talk about anything about bulkiness, nothing about stereo hindrance. Forget all that. Just talk about stability. So guys, let's answer this in a more systematic way. If this particular carbocation undergoes SN1, what does that tell you about this carbocation? Stable or unstable? Stable. It undergoes, right? So that means it is stable. So use that, okay, to answer this question. The carbocation is very stable. Why? Guys, it's primary one. Primary only have one alkyl group. How does that stabilize it enough? Not enough, it's just one alkyl group. So guys, why is it very stable? It has something to do with benzene. Okay, so I need you all to know from now on, right? This is a very common compound in your exam. It's directly attached to benzene. So what happens? Just now you all mentioned delocalized pi electron cloud. Good. But the delocalized pi electron cloud is in the benzene ring one, right? How is that related to the carbon with the plus charge? Okay, good. Good. Okay, not the pi, but the, what's this thing called? All these it's p orbitals. Guys, remember, the p orbital is in this carbon also. So what happens? It's directly beside the benzene. So what happens? The p orbital of the carbocation will pretty much overlap with the one in benzene. Now that they're all connected, then what happens? Imagine now they're all connected as one family. Now what can happen? Now that they are family, then they can share electrons. It's like you probably want, okay, maybe thought of a bad example, never mind. Okay, so imagine this. Okay, you are connected everywhere. What? I thought of sharing food, but I realized you share food, not people that are not. Okay, whatever. Okay, never mind. Okay, so the idea is you must explain it this way. Okay, let's explain separately. The p orbital of the carbon with the plus charge overlaps with the what? Guys, fill in the blanks. Overlaps with the what of benzene?
The orbital.
It's not just p orbital of benzene. Okay, good. The whole thing is a system. It overlaps with the pi electron cloud of benzene. Okay, they overlap already, then what happens again?
Which then it forms like a system.
Okay, now they're all connected already, then the electrons can delocalize. Okay, where does it delocalize from?
That ring to the.
Good. Guys, take note, delocalization also follows the idea of rich to poor. So, who is rich and who is poor? Benzene is rich, the carbon, the plus is poor. So, you all need to do this. Okay, the direction is from benzene to carbon. Okay, thus, high electrons from benzene can delocalize into the carbon with a plus charge. We move this or write that later again. Okay, then so what? Oh, before that, okay, correct, but before that there's something. What will happen to the plus charge now? No, nothing about it. What happened to the plus charge? Not say gone, you'll never be gone. It's dispersed. Okay, take note, guys. This is poor, right? The benzene is rich. Can you see the benzene is supplying the guy with electrons? You supply him with electrons, he is gonna be dispersed, right? Okay, so you must first tell me the plus charge is dispersed. Okay, you're not comparing with anything, it's just a standalone compound. So just say plus charge is dispersed, thus stabilizing the carbocation, which then allows it to undergo SN1, right? You don't need to mention that. We can stop here. It's a unique answer. Okay, this is a unique answer, right? Because of benzene and because of delocalization. Okay. The orbital overlaps with high electron cloud. Okay, high electrons can delocalize into the carbon. Remember, it's from rich to poor. Okay, disperse, really stabilize. Highlight keywords once again. There is a question exactly showing this structure in the tutorial, so you should know already. Okay, I'm doing this, I'm giving questions now because there's a chance that we might not even have time to cover this even in the tutorial lesson. So might as well. Okay, now try the second one. Yeah, I know the question said that halogen alkane, but I purposely just draw the carbocation straight, more straightforward. Okay, good. Correct train of thought. Yeah. Doesn't undergo SN1, meaning it's not stable. That good right there is not stable. Your job is to answer why. Why is it not stable? Not undergo SN1 means not stable. Okay, can you all get the first idea? I think you all got it, right? It cannot undergo SN1. SN1 is for stability. So if it doesn't undergo SN1, it means it is not stable. Your job is to answer why this is not stable. Come, we look at the train of thought first. If it's not stable, that means the plus charge is intensified. Can you see that? Now, plus means rich or poor? Poor. So intensified means the plus charge becomes bigger, right? It becomes more poor. And that's a bad thing. Why would you want to become more poor? So write that down. The plus charge is intensified. Who do you think, right, is intensifying this positive charge? Okay, guys, you all notice I purposely draw 3 O's, right? OH. Okay, I know, right? These are immediately bonded to it like alkyl groups. I know. But let's follow the question. As OH. OH is what effect? Okay, just now alkyl groups are electron. Wait. Alkyl groups are electron donating. OH group is?
Electron withdrawal.
Yes. Okay, why is it electron withdrawing? Resonance, no delocalization here, so no resonance. Okay, in fact, this is the inductive effect. Why? Because inductive effect looks at the, you just write down. Inductive effect looks at electronegativity difference. Guys, let's recap this. This one we went through in theories also. Okay, carbon or oxygen, who is more electronegative? Oxygen. So imagine you press the dipole moment going towards oxygen. All three of them are, can you see? They are stealing electrons away from the center, the carbon with the plus charge. Can see that? It's because it's more electronegative. He takes electrons, they steal away. You want to steal electrons from someone who is poor, that's then bad, right? That's poor, right? Someone poor, you're gonna take money from, right? Okay, that's correct. Okay, so guys, look at the reason here. Okay, due to the presence of electron withdrawing OH groups, okay, the plus charge is intensified, destabilizing the carbocation. So what? Okay, thus it does not favor SF1. But I feel must put in your cheat sheet. So. Okay, so answer, of course, don't just copy. Try to write down the answer yourself. Okay. Oops. Oops, yeah, time to go through a few more things. Notes may have a little bit before we can finish. Maybe next lesson we need to finish a little bit. Okay, I could rephrase the question, right? And if I rephrase the question, whole thing different already. Okay, so no need to write down whatever I'm going to do now. You just try to answer, right? Perhaps I change the second question. Okay, bye-bye. Okay, anyways, you notice for both questions I talk about SN1, right? Yeah, I didn't write SN2 in any question here because SN2 is very simple. Just tell me how many bulky groups there are. Yeah, okay, so I'm more interested in the stabilizing of carbocation. Okay, so I think that one more important. Any questions so far? Okay, look at page 29 now of your notes. This is a summary table. Of course, it's useful, but it's not as comprehensive. So can you all take a look at it? We're gonna summarize everything together. Okay, we've gone through all the properties, SN1, SN2, a lot of shit happening. Okay, so there's SN1 on the left and SN2 on the right. Right? Okay, so first of all, rate equation. We'll write down the rate equation for both SN1 and SN2. Okay, just write Rx. Nucleophile, just write Nu for nucleophile. Right? Okay, we are. The first one, again, let's go through. Rate is equal to just K times Rx. Rate equals to K times Rx and Nu. Okay, remember the SN2, the 2 represents 2 reactants. There's no step. Okay, so guys, the rate equation looks simple like that, right? Okay, but okay, this one will look at more tutorial questions. Okay, but which one is affected by the nucleophile? So you increase the nucleophile's concentration, the rate will also increase. Which one? K2. Okay, so we'll go write this down. The rate is affected by concentration of nucleophile. But for the first one, SN1, not affected. Meaning as you can put so much nucleophile inside, you will not change the rate. Okay, a bit hard for us to see the importance now. When we do some questions, then we will do this. Okay. Now for stereochemistry, SN2, remember what happened to the stereochemistry?
Yes.
Okay, it gets inverted. So just write it down. Okay, SN2 inversion of stereochemistry. Why though? It's because of who? Because of what? What little feature? Something caused the whole thing to flip one whole. What happened? At the very first step, how does the nucleophile attack?
From the back.
From the back. Okay, it's because it attacks from the back, the whole thing flips. Okay, due to real side attack of nucleophile. Okay. What's the special feature of SN1 stereochemistry? You form a what? Okay, yeah, intermediate all that. Okay, racing mixture. Correct. Okay, it's regarding stereochemistry lah. Right? So racing mixture is formed. Why? It all started because of what? You're looking at the origins. Okay, good. We have a carbocation that's trigonal in shape. Okay. Next, what's next? Okay, number of steps. Okay, so SN2 has how many steps? One step. Why is there only one step? What do we produce? Transition state. Again, it's because of transition state, that's why it's not called a two-step reaction. On the other hand, SN1 is two steps, but why? You form an intermediate, it's legit, it's real. Last but not least, okay, the preference we went through just now already, so this one should be easy. Okay, SN2 primary, SN1 tertiary. Why SN1? Okay, why primary favors SN2? Okay. High or low stereo hindrance? Low. Okay, the full explanation just refer to your table. How about tertiary? Okay, stability is a stable, more stable carbocation. Okay, because the positive charge is dispersed to a large extent, whatnot. Right, that's your summary table. In this one, you can check yourself, you can write it down yourself also. Okay, can? Right, we have about 10 minutes left. Okay, and in this 10 minutes, I'm not going to go through much more content. Okay, so the next page will content very fast now. Okay, after that, we can do some tutorial questions from last week. Yeah, okay, can? Yeah, last week we did the reaction synthesis. Maybe you try that, okay, see how it does. Okay, any questions? No, okay, look at page 30, then I won't go over the next part already. Next lesson we go through. Okay, on page 30, we have rate of reaction. Guys, we have all the different types of halogens, right? And this one only dependent on one thing, bond strength. Yeah, that's it. Okay, there's nothing much to go through here. How do you explain bond strength? It's dependent on what? Not just bond energy. How do you explain why bonds are stronger or weaker? Good. Okay, to form covalent bonds, orbitals must overlap. So how strong a bond is depends on how much it overlaps now, right? So effectiveness. But guys, before we talk about effectiveness, how do we compare? Larger atoms overlap more or less. Larger atoms overlap less. Smaller atoms overlap more because more compact and stuff. Right? Okay, so always look at the flow. Look at the atomic radius. And then you compare effectiveness. And then you compare bond strength. Now guys, we are going to relate it to rate. Okay, for rate, right? A stronger bond, is it faster or slower? Okay, slower. Stronger bonds, slower, weaker bonds, faster. Because at the end of the day, right, we are just breaking the CX bond. Okay, go through the flow first, then we relate it to rate. Okay, come. Atomic radius, down the group. Out. Okay, good. Down the group, atomic radius increase. What happens to effectiveness? Increase or up or down? It decrease. Larger cannot overlap as well. What happened to the bond strength now? Less effective. If the bonds become weaker, the rate becomes, okay, because it's like kind of easier to break, right? So in other words, CI is the weakest, the fastest. Okay, the rate we will see in the next lesson more. Okay, Ken? Okay, come, we have time, we still have a bit of time, right? I want to do like maybe one tutorial question, not very, no application, okay, quite chill one. Okay, I'll just share first.
Yeah.
For the one you all do now, I think we'll give up. It's a 12, I think. Yeah. The what? Okay, come. Guys, let's do question 3. Yeah, level 1. Okay, level 1, question 3. I just need it's concept check. There's no application or anything. Okay, just question 3 first. Okay, I'll do part A. Okay, we do part A first, then we can do B part 1. Then we finish for today. Okay, 3A and B part 1.
What?
Okay, skeletal, by the way. I don't think I have to say that right now. Okay, skeletal.
It's positive. You can start with OH, I think. Wow.
What nucleophile do you want first? Okay, not so just put NaOH. Yeah, Na is just a spectator ion. Right, so just put OH minus. Okay, do you remember? Do we need to repeat it?
No.
Yes, must. Okay, if you are breaking the bond, you have to break first, then you can replace. Okay, guys, you're breaking a sigma bond. Sigma bond I explained last lesson must break up. The sigma must use heat. If it's pi bond, no need heat. Okay, once you're done with that, I'm sure you can try it before. Not a difficult question at all, because they even tell you it's SN1 already. Okay, in other questions, you need to figure out whether it's SN1 or SN2 yourself. Okay, you want to draw the structures first, right, of C and D. Then you do reagents and conditions last. Yeah. Okay, reagents and conditions first, unless you can see what to draw now. If not, you wouldn't know what reagents. 3A, 3A. Yeah, correct. Yeah. Okay, when you all draw mechanism, please try not to refer to the notes. In paper? Alright. Anyone else need paper? going to review the answer for part A. There's an O here, so you should know there's the closed sub. Here, the VR is removed, so this is elimination. Okay, now this question, did it say anything? No, okay, guys, how many possible answers are there for E actually? I realize they never specify anything, so very easy question. Okay, best one to draw is this. Guys, you realize, right? There's other ways to eliminate. You don't need to remove a H from here. You can also remove a H from here. That means the double bond will be here instead. But this is a minor product that we went through last lesson. Okay, this one also can undergo the cis formation, which is correct also, okay, but not as common as trans. This one has less steric hindrance compared to cis, remember? Because this one, the groups are on opposite sides of alkyl groups. The same side alkyl groups, more steric hindrance. So the best answer to draw is still this. Okay, not that they will mark you wrong over here. If they specify, which they probably will in exam, okay, then you can draw this. Okay, ratios and conditions, this one nothing for me to go through. NaOH equals heat. Second one is ethanolic NaOH and heat. Okay, you notice it's just one solvent away. Right? Okay, one uses water, the other uses ethanolic, and it changes the whole reaction. Okay, next is the mechanical. You can write that in classes. Or just write. Okay, but certain teachers, right, it might be quite strict about heat versus heat under reflux, even though it actually does that. So the one, right, if your school notes, right, heat under reflux, but you right. Okay, heat under reflux and heat usually is the same, actually no difference one. Yeah. Okay, reflux is just the process used to heat the thing. So you don't technically need to specify.
Yes.
Yeah, talk about all this, right? Yeah. Right? Okay, because there's this thing called 6S rule. It's not an important rule, but basically this guy, right, say that, okay, let's listen to him, he's dead already, but okay, he says that if you have more alkyl groups bonded to the double bond, right, it's better. So this one has 2 alkyl groups bonded to the double bond. This one only has 1 alkyl group bonded, so it's actually not as good as this. Okay, you never need to explain the 2 versus 1 shit. It's just a internal thing.
Oh.
Right? Never need to explain. If not, I would have emphasized. I'll just very briefly go through this. Yeah, just no care. Yeah, you can say so. As a product of elimination, I mean, by itself can be, yeah. Okay.
Are there more?
Okay, this is the setup. SN1 very easy. Okay. So you practice SN2 just now already. Okay, now it's SN1. I need to first see the partial charges and the bond breaking without any provocation. Okay, you form a secondary carbocation. Again, secondary, right, can undergo a mixture, but this question very easy because they tell you what it undergoes. Harder questions, right, they will not tell you what secondary undergoes, and then you need to look at the clues. Like for example, SN2 got how many reactants, something like that. Okay. You see, I purposely squeeze the arrow until it's pointing at the carbon. Okay, that's the answer. Okay, we'll check your details. Okay, any questions so far? Just nice, we finished. Wait, what? Am I tripping? Yesterday I cut my nails. They only cut one hand.
Huh?
Wait, what? How does that happen? That's never happened. I was wondering how come my nail here so long? I guess. Yeah, very crazy. What's going on? Just take it, yeah, look,
But it's.
I'm going crazy, I'm going crazy.